So welcome everyone. We are here again for Math7502. This is our last session of the semester. And what we'll be doing today is talking about a few topics that, well, a couple topics that will be potential topics for your project. Isn't that right, Walla? These are project topics that we're doing?
No, I think.
No?
About gradient descent and
Oh, so these aren't options in the project? Okay, well, you all have the PDF on your task description. What we're covering tonight is, well, I'll be doing gradient descent, otherwise known as steepest descent. Walla will be covering Gaussian distribution.
Yes.
Okay, Gaussian distributions. Sure, so I should begin immediately. Okay, so what I have for you is a, well, I guess this comes from my lecture notes on teaching another course here called Math7502-UQ on this topic. So it'll make it easier for me to describe things for you if I just go through some of this, okay? So steepest descent. Now the idea, I mean, there you see me chasing after a ball. And balls, you know, is when they roll down, well, they roll downhill. If you just let it go on the side of a hill, it rolls downhill, right? And sometimes it gets stuck in a pothole. There's a pothole there where, you know, it falls to a local minimum, okay? So that can happen in steepest descent too. But the main idea is to go downhill until that path. So go in a direction downhill, just like that arrow does, until that path takes you somewhere that's not going downhill anymore, right? So in other words, eventually you've got to do a minimization problem intermediately, right? But this is all part of that algorithm. All right, now to go downhill, you go in the direction of minus grad f, right? Because grad f tells you which way to go in order to go uphill at the fastest possible rate, right? So minus grad f, that's the direction to go in order to go downhill. Okay, so I'll scroll on to my next page. And then since I'm in a little bit of a hurry, so I want to give Walla plenty of time, I'll go to the main points, all right? So if you're going to go downhill, so that's minus grad f. Now, if you have a three-dimensional surface, this is, you have something like f equals a function of x and y, right? And so what you get out of taking the gradient vector is you get a vector with two components, right? So it's like a compass heading. If you're on, for example, our local mountain, Mount Kutha, and you had a blindfold on, let's say, and you wanted to know which way to go downhill, you might, you know, read your magic compass, and it would give you a two-dimensional heading, right? Okay, so that's my analogy for this. It's a vector with two components in it. Now, so we form a sequence, basically. The next point in the sequence, now notice I've got superscripts with brackets around them, so those are not powers. Right, so here it is. The next point in the sequence of points is the previous one minus grad f of the same previous point times this scalar lambda subscript k. Okay, so this is the general description of how we get to the next point. But this lambda subscript k here is something that has to be worked out, okay, in order to stop when you're not going downhill anymore. All right, so what I want to do, I guess I got my hat here. So if I take my hat, well, you all know what a hat looks like, right? But the inside of it, we have this bowl-like shape. So if I follow one of these, I go down, right? But at a certain point, I'm not going downhill anymore. I start to go back up, right? So that's my analogy there for what's going on. You want to basically minimize this with respect to lambda k. All right, so minimize the function with respect to lambda k. And so we take a first derivative with respect to lambda k. Now, this is just basic differentiation here, as in d on d lambda k of this expression. All right, so in other words, find the lambda k such that this derivative is equal to 0. Okay, so that's the calculation that I'm displaying next. So what we have here is we apply the chain rule. Now, this is the chain rule involving partial derivatives. Okay, so let me pull out a pen and I'll just remind you. We've got f subscript x and then dx on, and then, hang on, how's that go? Yeah, you gotta make them look like as if they were fractions, then they would cancel, okay? So here then I want d lambda k, right? Okay, fy dx on d lambda k. Okay, so that's this one, this dot product here. So the gradient vector involves these two partial derivatives, and then this is the derivative of the vector x superscript k plus 1. Right, so this is just the chain rule involving partial derivatives. All right, now expanding that out, we substitute in the description for lambda k plus 1 there and there, okay, and then we simplify this. So taking derivatives, we end up with this. So grad f, now this is xk plus 1 inside the bracket still, and then this here is minus grad f of xk. All right, so this is meant to be 0 because we're seeking the lambda k such that this first derivative is 0. So what this tells you then is that these two gradient vectors should be perpendicular to one another, right, or orthogonal. They have a dot product of 0. Okay, so that gives us a nice diagram to think about. And then I've rewritten the same thing in a simpler form. All right, so we can find lambda subscript k and thereby find xk plus 1, repeating the procedure until we get reasonably close to a minimum. All right, so if you were to program this in a computer, you might use a while loop, and then you would break the while loop when the next point is not so distant from the previous point, right, according to some tolerance. Okay, so moving on. I'll pull up another page. It makes a lot more sense once you see a simple example. So that I'll show you here. Okay, so here we've got a function of two letters x and y, and we're going to find the minimum of the function using steepest descent. And let's use this initial guess. x0 is 1 comma minus 1. Okay, so what we do, we take the gradient vector, right, which is right there, simple to calculate, substitute in 1 minus 1, so this is our x superscript 0, okay, and then we simplify that, we get the point 12 minus 15. Okay, next, the next point in the sequence is x1. So this is this point x0 right there, 1 minus 1, and then minus lambda subscript 0 times what we just got, 12 minus 15. Okay, and then we add these together. We have this simple linear relationship, and this is a point in terms of lambda 0. And now what we want to do is find the lambda 0 that minimizes that derivative that we looked at. So in other words, we want to find something that's perpendicular to f of x superscript 1. Okay, so subbing this in, right? So we basically take this as our x, this is our y, we sub it into the function. We get this polynomial here, right? And then we can just differentiate that, right, symbolically. So here's the derivative. And now, of course, you want to know when is that derivative equal to 0. All right, so differentiating, and you find that there's only one real root and say 2 complex roots. So we take the real root here and we get this lambda 0.04, etc. Okay, we use that in the description of the next point and we get our x1, right, just in that way. All right, but there's another way to do this, which is perhaps simpler. Okay, so what did we have? This is our x1 inside the bracket. So grad f of x1 is this. It's still a little bit lengthy. And then we just seek lambda 0 such that it's perpendicular to 12 minus 15. Okay, so I mean, that gives us another way to do this, because we have this here and then we take a dot product. We wish this to be perpendicular to 12 minus 15. All right, so you can kind of do some of that in your head. All right, so so again, we have, this is our x1, and then we just repeat until we see that this sequence is converging to a point, right? And so that, that point that it would converge to would be a local minimum, I guess, right? Because remember, if you go back to the picture of me dropping a ball down the hill, sometimes that ball got stuck in a pothole along the way, right? So that can happen. It can just find a local minimum. So you really kind of have to know your surface as well. All right, so now I want to show you a contour diagram. Okay, so here is the same surface. And so basically, geometrically, what's going on is you're going in some direction, right? So suppose you began your sequence here at x superscript 0. You go downhill, right, which is perpendicular to the contour. And maybe, if I'm really clear about it, maybe you're starting here so that it looks perpendicular. Okay, you travel in this direction until until you start to go uphill again, right? Because you don't want to you want to stop when you're not going downhill anymore. All right, now that happens to be perpendicular to a tangent to some other contour. All right, so you stop there, and that is finding your lambda. And then you turn this right angle and you go downhill again until you're not going downhill anymore. You stop at a contour, and it might be here. So this picture doesn't show all of them, of course. And you repeat and you repeat and you repeat, and hopefully you end up at the local bottom, right, which will be where all of these contours become a point. Okay, so I hope you get the idea from that of what steepest descent is. Now, where are my, okay, the algorithm, which looks something like this. To implement this on a computer, now remember, well, actually, I'll skip that comment. I was going to say, in your project, I understand you have to write some Julia code, right? But if this is not a project, potential project, then you're not doing this. But you still might want to know how to implement this. Okay, so you define functions for, you define your functions. F, that's the one you want to find your minimum for. And then, so let G be your gradient vector, which I guess you could do symbolically or numerically. Define a function h of x, which inputs a guess point and outputs f of p minus lambda g of p. Remember, g of p is the gradient at p. All right, your next step, define a function k of x, which inputs a guess point and outputs the first derivative with respect to lambda. Define a function L, which finds the least positive lambda satisfying first derivative 0. Now, you could use Newton's method of finding roots, for example, if you wanted to do that numerically. All right, so next, define a function. You might call that nu. It's a function of x, inputs a guess p and outputs the next point, which will be just this one, p minus phi g, all right? So that's the same phi there. Then you want to use a while loop setting z is equal to the new x, calculate the norm, so that's Euclidean norm of z minus x, and then set x equal to z so that you can repeat this procedure, right? Of course, you exit if this is close to zero, close enough to zero as compared with some tolerance. Okay, so having described the algorithm to you, and maybe you did this in lectures already, I'll move on to do some discussion of some things in a book by Gilbert Strang, which is one of your course texts. Now, let me see if I can find. All right, I guess I don't have the actual problems with me now. So let's have a look at them. Maybe I've got it written here, so let me see. And I think I should zoom in a little more because this is small type. All right, so this is in Strang. It's example 3 on page 364. So it says, basically says, let S be a positive definite symmetric matrix, and let f of x be given by 1/2 x transpose x s times x minus a transpose x. Okay, so the claim here is that the minimum is x star f minimum, and it's equal to this. So the claim is that the minimum is this point. So S inverse A, and then minus 1/2 A transpose SA is the actual minimum, right? But this is where it's found, S inverse A. All right, so occurring when the first derivative is 0. All right, so we want to calculate grad f. All right, we find grad f. So these are subscripts here. You probably can't see this clearly unless you zoom in. But what I've got is f subscript x1 and then dot, dot, dot. Of course, I mean this to be a vertical dot, dot, dot. And then we stop with f subscript xn. Okay, so we're meant to get sx minus a. And then so solving this would give us S inverse A, like what we have here, right? But I think what I'm going to do next is show you how to arrive at that with a 3×3. So if you had a 3×3, now this is general, but if you had a 3×3, then you might find this easier to think about. Okay, so let's write a symmetric matrix S that's 3×3. So you can see it's symmetric there. A13 there, A13 down the bottom. Okay, and so on. So let's first construct the ternary quadratic form given by this expression, right? So basically, you put in your x1, x2, x3 as the uppercase x that I have there, the vector. Then I'm going to say let A transpose be alpha1, alpha2, alpha3. All right, and so basically what I'm doing here is I'm using Mathematica's symbolic capabilities to help me out with that calculation. All right, it makes some short work of this. So essentially you can see this, and it looks like mathematics, but I'll put my fingers over what you don't want to look at just yet. So 1/2, then we've got x transpose, then we've got our matrix S, then we've got x, and then we've got A transpose, and then we have X, all right? So we're subtracting that. So it's exactly as above. Now what I'm doing next is I'm just saying, please expand that, Mathematica, and then I end the bracket there, right? So you get an expanded expression, but it's got too many brackets in it. I just want to pull out the scalar. So that's what I do at the end. I say, take out the first element of the first element so that I just get the scalar there. Okay, and I'm going to call that F. All right, so next, and that'll come out and I'll show it to you in a moment, but next you will construct the gradient vector, right? So that just takes partial derivatives. Again, I can do this with Mathematica just using the uppercase D, right? Because that F is this one that's already in memory at that point. So this is the gradient vector there, all right? And then that will be displayed as well. And so what I'm saying next, express this grad f equals 0 as a matrix equation. So let's do that. All right, but first I'll show you all of the outputs of this because I've got them right there. All right, so here's our f. All right, so you can see it's a ternary quadratic form. I've got x1, x2, x3, and the powers are squared. Well, the leading powers are squares. Okay, below that we have the gradient vector there, and so you can see it's a linear expression And there we have commas, comma there, comma there. All right, so that's our f that got used in this calculation. And so what we want to do is express this part here as a matrix equation. But I've got that just written right there, right? Because you can see if we multiply this out, A1, A2, A3 times each of these, add those together and subtract each of these one by one, right? So that gives you exactly this. So what we see is that this equation, grad f equals 0, is exactly this one, right? Just as claimed right there, okay? And so now this is our s, this is our x, this is our a. So multiplying by the inverse, we have the claim that s inverse a occurs when the first derivative is 0. All right? Okay, so now there's a bit more to that, but again, I don't want to go on and on and on about the one question. I just want to point out a few things for you to make that topic a little easier for you. All right, so let's move on to the next one, and I think this will have to be my last example before I pass it on to Walla to give her enough time to talk about her topic, Gaussian distributions. All right, so this one's on, I need to, right, put it in view. Okay, so this one is the same book by Gilbert Strang, this time page 348. It's called an important example with Zig Zag. Okay, so here we've got a very simple function. F of x and y is 1/2 x squared plus b y squared. This function is extremely useful for b between 0 and 1, b greater than 0, but less than or equal to 1. Okay, so the gradient vector here, that's simple to calculate. It's x comma by. And it turns out, quite obviously looking at this, right, that 0, 0 is the minimum. And it satisfies grad f as 0. Okay, so we can see immediately putting in 0, 0 gives grad f equal to the 0 vector. Okay, good. So let's go into more details. Steepest descent with exact line search produces a simple formula for the sequence, right? But what we're talking about is a closed form for the sequence that converges slowly to 0, 0, right? So this is basically trivial to see that this is the bottom of this in one calculation, but the discussion is about what steepest descent does here. Okay, so next and last page, basically. All right, so I'm just going to go through some of the details of the calculations involved in the steepest descent here. All right, so we've got our description of the sequence. This time I'm using subscripts, just like what is done in Strang's book. Okay, so there's the description of the sequence, sub in grad, formula for grad, combine those, right, and then simplify. So here we've got 1 minus lambda times x, 1 minus lambda b, and then all times y. Okay, so where these two are perpendicular. So what we have here then is taking that dot product, we have 1 minus lambda k, xk squared, and then plus 1 minus lambda k b, yk squared. This should be equal to 0. All right, so rearranging that, we have this so that we can expand and collect in terms of lambda k. Remember, we want to solve that. I think I need to zoom in a little bit more because this type is so tiny. All right, so I get this, if I've done that correctly, and I think I have. All right, so using that now, I want to sub it into this expression, remember. So subbing that in, I have this, and now I want to take that difference and put it under a same denominator. Okay, so there I've done it below. All right, moving on. So now in Strang, it says starting with b comma 1. But when I do that, I don't get the same thing. So one of us has a typo, I think. I'm not sure. It might be me, right? But then when I try to go and look for typos, I go through all the same thoughts. I don't know, maybe you're the same, and then I get the same result, right? So, okay, but anyway, x1 subbing in this with b comma 1 dot dot dot. This is the calculation with that one, and I find that there must be a typo because it doesn't quite agree with the text in Strang's book. So I decided to try to guess what he meant. And that is assuming I'm the one who's right, but I could be the one who's wrong, right? Of course. All right, so starting with 1, 1 instead, I get a simpler looking formula. So I get x1, y1 is this, x2, y2 is this. And so I have quite a nice pattern going. x3, y3 is this, and so on. And then xk, yk is this. So now I have a closed expression for the points, right? And the powers are k. All right, so next, f of xk, yk, subbing everything in. We have this, and then we want to simplify so we can factorize, and then we can express this in the following way. Okay, so where f of xk, yk is 1 minus b over 1 plus b to the power of 2k times f x0, y0. Now, I believe that's only the case when we start with 1, 1. All right, so basically, now it almost agrees, right? I think it pretty much agrees with what Gilbert Strang has in his book there. But the following page talks about what happens, right? And so I'll just go straight to this. So basically, what's going on to make this converge slowly is we have all these little zigzags, right? And so we're taking these little steps, just like this, and it's slowly. Eventually, its path is tangent to a level set L. All right, descent stopped. And that basically means that you're within your tolerance, right? Now, you, the programmer, set your tolerance, of course. Going further will increase f. The first step ends. All right, so he's describing the procedure that I've already described just a little bit earlier. All right, so I think I'm just going to pause here because Walla looks like she's ready and she has really much to discuss. So I'll turn it over to Walla now. So thanks, everyone.
Hi, now we need to move to Gaussian distribution. We need to talk about 3 different types: univariate, bivariate, and multivariate. Just we need to know the brief definition about univariate and bivariate, and we need to talk about multivariate. What is the Gaussian distribution? Gaussian distribution is the same as normal distribution. Is a type of continuous probability distribution for a real value problem, for a real valued random variable, and the density function for univariate is given by f of x equal 1 over sigma square root of 2 pi multiply with the exponential of minus a half x minus mu divided by sigma square. Here we have 2 parameters, mu, which is the mean, and sigma, which is the variance. We need to use Gaussian distribution to present real valued random variable, and it's like a bell shape. This is the univariate. I think all of you know about univariate distribution. You need to know univariate because we need to define bivariate. What's the bivariate? The definition of bivariate normal, if we have 2 random variables, x and y, we said that they have a bivariate normal distribution if a linear combination has also a normal distribution. So if you can find a and b, and the linear combination for ax plus by is a normal distribution, we said this is a bivariate normal. And we said it's bivariate because just we have 2 variables. Here we have x and y, both are random variables, and a linear combination between these is also a normal distribution. This is for all A and B belong to R. And if we need to find the probability density function, we need to concentrate here because here there is few details. We said here two random variables, if we have x1 and x2, are said to have standard bivariate normal distribution with correlation coefficient rho we call rho as correlation coefficient. And the joint BDF is given by, here we have f of x1, x2 equal 1 over 2 pi multiply with the square root 1 minus rho square multiply with the exponential of minus z divided by 2 times 1 minus rho square. And the value of z is given by x1 minus mu1 square divided by sigma 1 square minus 2 rho multiply with x1 minus mu1 multiply with x2 minus mu2, and this is divided by sigma 1 sigma 2 plus x2 minus mu2 squared divided by sigma 2 squared. If you look here, mu1 is the mean, mu2 also is the mean. So mean here is a vector, consists of mu1 and mu2. We have also rho. The value of rho, we call it as covariance between x1 and x2. I put here x and y, which equal the variance between the first coefficient and the second coefficient x1 and x2 divided by the first variance for x1 multiply with the second variance x2, and the value of rho between -1 and 1. In general, the covariance matrix sigma, we define that this function has two parameters, mu and sigma. The mu is vector because here we have two different random variable x1 and x2. Mu equal mu1 and mu2. And sigma, this is a covariance matrix which equal sigma of the first variable, sigma of x1 square, rho of sigma of x1 multiplied with sigma of x2. And here we have, because this matrix is symmetric, here we have also rho of sigma of x1 multiplied with sigma of x2. And the last one, we have sigma square of x2. So this is just a brief definition of bivariate, to know that in bivariate, we have x1 and x2. So in multivariate, we have more than two. We have x1, x2, x3, up to xn. We need to concentrate in multivariate, and we will explain more about multivariate. I think you know about univariate and bivariate. In multivariate, we said a random vector x, which consists of x1, x2, x3, up to xn, is a multivariate normal if any linear combination of the random variables x1, x2, up to xn is also a normal distribution. Before we talk about x1 and x2, if the linear combination between x1 and x2 is normal, we said it's a bivariate distribution, but here we have more than 1x, more than 2x. So we call it multivariate distribution. And we can write a linear combination as a1 x1 plus a2 x2 up to an xn. And a1, a2 up to an, all of these belong to R. There is two things you need to know about this multivariate. If x is a multivariate normal, the mean here, the mean is a vector, and the value of mean equal is the expected value for the first variable for x1, the expected value of x2 up to expected value for xn, and also the covariance matrix, which call it sigma here. This is sigma for I and j. This is a matrix. The value of sigma all the time equal covariance between xi and xj. And we can write it as, this is x, this function is a normal distribution with mean, mu, and sigma, which is the covariance matrix. Now, we need to know what's the BDF for this distribution. The probability density function of multivariate normal distribution is given by, this is the probability density function, which equal to, here we have 1 over 2 by to power n over 2, multiply with the determinant of sigma to power a half, multiply with exponential to minus a half. Here we have x, which is a vector, minus mu also, which is a vector transpose, multiply with a matrix, which is sigma inverse, multiply with x minus mu. This is vector also, because x here is a vector and mu also is a vector, where mu is the mean and sigma is a covariance. Now let's try to find the bivariate from multivariate. Here we have, this is the multivariate. Now we need to find bivariate from multivariate. We need to substitute n equal 2, and we need to calculate what's happened when n equal 2. We need to use, here we have the probability density function for multivariate is given by, here we have x, given in two parameters, mu and sigma. This is equal 1 over 2 by to power n over 2, multiply with the determinant of sigma to power a half, multiply with the exponential minus a half, x minus mu transpose, multiply with sigma inverse, multiply with x minus mu. Now this is a multivariate. We need to find bivariate from multivariate. So we need to substitute n equal 2. So let's substitute n equal 2, and we need to see what's happened if we substitute n equal 2. Because we talk about n equal 2, so the value of mu, just we have mu1 and mu2, and in x, just we have x1 and x2. So the vector mu here equal mu1 and mu2, and the value of x equal x1 and x2, and sigma, which is the covariance matrix, which equal sigma 1 squared, sigma 1, 2. Here we have also sigma 1, 2, and here we have sigma 2 squared. This is matrix equal to sigma 1 square, row of sigma 1, sigma 2. Here we have also row of sigma 1, sigma 2, and here we have sigma 2 square. If you remember, here we define the value of sigma, the same thing. Here we have sigma 1 square, row of sigma 1, sigma 2, row of sigma 1, sigma 2, and here we have sigma 2 square. The same thing. Okay. If you look here, we need to find the determinant of this matrix, sigma, and also we need to find the value of sigma inverse. This is 2 by 2 matrix, so we can easily find the value of sigma inverse. To find the value of sigma inverse, this is equal 1 divided by the determinant of this matrix, which equal sigma 1 square multiplied with sigma 2 square, minus rho square times sigma 1 square, sigma 2 square. If we can take sigma 1 square, sigma 2 square as a common factor, it's remaining just 1 minus rho square. And here we have, this is remaining the same, sigma 1 square. And here we have sigma 2 square. And we need to change the sign here. This is equal minus rho, sigma 1, sigma 2. And here we have minus rho, sigma 1, sigma 2. This is the value of sigma inverse. So let's try to simplify. If we need to divide every entry here, sigma 1 square, by sigma 1 square and multiply with sigma 2 square, just to simplify, we can write it as sigma inverse equal 1 over 1 minus rho square. And this matrix here, we need to divide sigma 1 square divided by sigma 1 square, sigma 2 square. You will get 1 over sigma 2 square. And here we will get minus rho divided by sigma 1, sigma 2. Here we'll get also minus rho divided by sigma 1, sigma 2. And here we will get minus 1 divided by sigma 1 square. Okay, this is the value of sigma square. Now we need to find this value. We need to substitute here. We need to substitute instead of x minus mu transpose times sigma inverse. And we found the value of sigma inverse times x minus mu. So just we need to substitute instead of x minus mu transpose times sigma inverse times x minus mu. This is equal, here we have x1 minus mu1, here we have x2 minus mu2, multiply with sigma inverse, which is here. We can write just this matrix, okay, and keep this constant out, multiply with this matrix, which equal 1 over sigma 2 square minus rho divided by sigma 1, sigma 2, minus rho divided by sigma 1, sigma 2, and here we have minus 1 divided by sigma 1 square, multiply with the transpose of this vector, which equal to x1 minus mu1, x2 minus mu2. So just you need to multiply these together, and you will get that, you will get P of x1, x2 equal 1 over 2 pi sigma 1, sigma 2, multiply with square root of 1 minus rho square, multiply with the exponential of minus z over 2, multiply with 1 minus rho square. Where is the value of z equal? Sorry, because we divide over these. Where is the value of z equal? x1 minus mu1 square divided by sigma 1 square minus 2 rho, multiply with x1 minus mu1, multiply with x2 minus mu2 divided by sigma 1, sigma 2 plus x2 minus mu2 square divided by sigma 2 square. If you look here, this is the same as BDF, which we got at when we have bivariate. This is the same as bivariate distribution. So just we need to substitute n equal to, try to find the value of sigma inverse and substitute in the BDF for multivariate. You will get the BDF for bivariate. So this is the value of bivariate normal distribution. Okay. Let's move to another thing. If we define something called the correlation matrix, the correlation matrix is given by, this is called a correlation matrix. We call it R. The entries of this matrix, we have an expected value of x1 square. In the diagonal, we have the expected value of here x1 square, x2 square, xn square. And here we have the expected value of the multiplication between x1 and x2 up to the expected value of xn, x1. Here, the same thing, we have expected value of x1 times x2 up to expected value of x1 times xn. This is which we call it a correlation matrix. This is a correlation matrix. And if we define the covariance matrix, and we talked about covariance matrix before, but just for 2 by 2. Now, if we have n by n matrix, the covariance matrix, we can call it K. This is equal the expected value of x1 minus mu1 squared. Here we have expected value of x1 minus mu1 multiply with x2 minus mu2 up to expected value of x1 minus mu1 multiply with xn minus mun. If you look here, we have in the diagonal, here expected value of x1 minus mu1 squared. Here we have expected value of x2 minus mu2 squared. Here we up to expected value of xn minus mun squared. Okay, there is some different properties for these two matrices, for correlation matrix and for covariance matrix. If you look here, both two matrices are n by n matrix. The dimension for this matrix is n by n. And the dimension for covariance matrix also is n by n. And both matrices are symmetric. The first one and the second one, both are symmetric. The second thing, the diagonal elements, diagonal for this matrix, here, these, are equal to the variance of x, because the variance of x equal the expected value of xk minus mu k squared. So the diagonal here is the variance. The third thing, if the elements are uncorrelated, if these x, here we have x1, x2 up to xn, if these are uncorrelated, then the covariance between any two equal 0. If we have x1, x2 up to xn, and these are independent and are uncorrelated, so the covariance here equal to 0. The fourth thing is, if the vector of the expected value is 0, here we have expected of x1 minus mu1 squared. If this mu1, the expected value of mu1, for example, is 0, the expected of mu1 is 0, that means here we can call it as mu k. This is here, mu1, mu2, and suppose it's here up to mu n or mu k. If this is equal to 0, and the expected value of xk equals 0, then you will get that the correlation matrix is the same as covariance matrix. If you look here again, if this one is 0, is the same as the first matrix. Okay, if you put m1, m2, and up to mn, all of these are 0, which means expected value of xk or the value of mk equal to 0. So the matrix R is the same as the matrix K. The last thing, or the last property here, xk is a diagonal matrix if the random variables x1, x2 up to xn are independent. If you have many random variables and these random variables are independent, we will get just a diagonal matrix. You will get just an interest in the diagonal, and the rest everything is 0. Let's try to solve an example, talk about these properties. Okay. Here we have an example. They give you, let x consist of 3 vectors, 3 random variables. Because here we have more than 2, we call it multivariate. Let x equal x1, x2, x3. Be the jointly Gaussian random vector. We need to find the expected value of x and the matrix K. The joint BDF is given by, this is the joint matrix. Here we have f of x1, x2, x3 is given by this function. They ask you to find the expected value of x. If you look here, the exponential here give you the relation between x1 and x2. There is a relation between x1 and x2, and there is the value of rho between x1 and x2. But here x3 is independent from x1 and x2. So here x3 is independent. And because we talk about Gaussian random vector, x3 is a normal distribution with mean equal 0 and with variance equal 1. And it's independent of x1 and x2. And it is independent from x1 and x2. If you look here, we have x1 and x2. There is a multiplication between x1 and x2. And x1 is a normal distribution with mean 0 and variance 1. The same thing for x2. x1 and x2 both are a normal distribution with mean equal 0 and with variance equal 1. If you look also, the value of rho equal -1 over square root of 2. This is from equation also. It is the same here, which equal -1 over square root of 2. If you know the definition or the VTF or multivariate, you will find that this is the value of rho. This is here, the value of rho. So the value of rho equal rho between x1 and x2 equal -1 over square root of 2. And from the definition of the value of rho, this is equal the covariance between x1 and x2 divided by sigma 1 and sigma 2. Because x1 and x2 both are normal distribution and with variance 1, so sigma 1 here is 1, sigma 2 also is 1. So this is equal covariance of x1 and x2. So the vector of expected value is mu x equals 0. Now we can write the matrix xk, which equal to, we have in the diagonal variance, and we said that x1, x2, x3, both three are random variables with mean equal 0 and variance 1. So we need to put 1 here, 1 here, and 1 here. And we know that there is a relation between x1 and x2, and there is rho contact between x1 and x2. So here we need to go to put -1 over square root of 2, and here we need to put -1 over square root of 2, which is the same as the value of rho. The rest is 0. Why? Because x3, it's independent from x1 and x2. So this is the value of k. Okay. The last thing, now we need to develop. Now we need to develop compact expression for R and K. Let's find the value of X times X transpose. Here we have the value of X, which is a vector. The dimension of this vector is n times 1. Multiply with another vector. The dimension of this vector is 1 times n. If you multiply these together, you will get this matrix. This matrix is n by n matrix. We need to find the value of expected value of this matrix. We need to find the value of R, which equal the expected value of X times X transpose. Why we need to find that? If you look here, the interest is similar to matrix R, just we need to take the expected value for each entry. Because here we said before, the matrix R, here the matrix R, the same thing, the same as X times X transpose, just we need to take the expected value for each entry. Let's try to find this value, the expected value of X times X transpose, and the value of K equal the expected value of X minus mu K multiply with X minus mu K transpose. The first step, we need to use some properties here. X minus mu K, we can write it as X transpose minus mu K transpose. This is equal expected value of X minus mu K multiply with X transpose minus mu K transpose. Then you need to expand. This is equal expected value of X times X transpose minus mu K, because it's a constant, multiply with expected value of X transpose minus expected value of X multiply with mu K transpose plus expected value of a mu K times mu K transpose is the same, which equal mu K times mu K transpose. If you look here, they are the similar. This one and this one is the same. And the expected value of X transpose equal mu K transpose. Expected value of X transpose equal mu K transpose. So just we need to simplify. Here, this is expected value of X times X transpose is the same as the value of R, this is equal R, minus mu k times mu k transpose, minus mu k times mu k transpose, plus mu k times mu k transpose. This is equal to R minus mu k transpose. This is the end. Yeah, thank you for coming. Is there any question?
Nice work, yeah. And you need some water.
Yeah, I think I'm putting with myself because there's just.
Yeah, well, it's okay, but maybe people will see this later.
Yeah.
Nice work.
Thank you.